Hi guys, this is Miss Hubbard. I'm going to talk about the second part of chapter 2. So this part is talking about energy. So most of the energy on the earth is due to the sun. The sun's input. Thank you, sun. We appreciate you. There's also energy already in the earth because the center of the earth is molten, and so we have a lot of heat energy there. So we'll get some energy from volcanoes exploding and things like that. But main energy source on the earth is the sun. So there's two different things we need to know about for energy is what energy is. Energy is the ability to do work. That means actually move something from one place to another. So even if you stood against the classroom wall and just started pushing as hard as you could, it would feel like doing work, but you're not. You're not moving something. So energy is the ability to do work. So remember that definition. Power is um, is defined as the rate at which work is done. So energy is going to equal power times time. We have a lot of different units we're going to use in this class. Calorie has to do with heating up a gram of water by 1 degree C, so that's called a calorie, and it's measured in joules. So water is actually pretty cool because it takes a lot of energy to raise it up. It has a high specific heat, so that's a good thing, and it helps keep our energy level on our Earth, our temperature level actually pretty stable, which is nice. The calories that we think about in real life are 1,000 of these small calories. So 1 calorie that you see on the food that you eat is actually 1,000 of these small calories. So calorie, a big C, is actually what we call a kilocalorie. So if you eat 2,000 calories, that's what we're talking about for this big calorie. We also will talk about British thermal units, BTUs. That's another way of measuring energy. And we'll also talk about kilowatt hours, which is the amount of energy used for 1 kilowatt of electricity for 1 hour. So those are the different units, and we'll have to convert from one to the other, and we'll do that in class. So remember, there's different kinds of energy, and they're all important. Kinetic energy is moving energy. Potential energy is the energy that's stored in something. So if you have a big boulder on the top of Mount Everest, it's not moving, but once it does start moving, it will give you a lot of energy. So that's called potential energy. It has the potential to give you a lot of energy. Chemical energy is what we were talking about in chemical bonds. It's potential energy that's stored in chemical bonds. So when you have chemicals rearranging themselves, which is called a chemical reaction, then you're going to get some energy. And temperature is the measure of the average kinetic energy of a substance. So temperature is actually moving energy. It's when you're putting a thermometer in your mouth to get your temperature, it's actually measuring how much atoms are hitting onto it and moving it, and that's a measure of kinetic energy. So, for example, this dam right here, the water behind here has a ton of potential energy because as soon as it goes over the spillway, and it's going to change into kinetic energy and give you all that energy, moving energy. So this is potential energy back here, kinetic right here. So let's talk about the first law of thermodynamics. It says that energy cannot be created or destroyed. That sounds familiar. That sounds like the law of conservation of mass. And you can't get something from nothing. That means you can't move something without giving some energy to it. So for example, this car, when you put chemical energy in the form of gasoline, you're going to get all kinds of energy outputs. So we're putting gasoline in a car, which is an energy input. We're going to get a bunch of energy outputs. We're going to get energy that we care about, which is moving the car, but we're also going to get a whole ton of other waste energies that aren't useful for us, but it has to happen because we've converted a high source of chemical that has a good source of energy, and we're changing it into another form. As soon as you change from one form of energy to another, you're going to lose energy in the form of waste energy, and a lot of times that's going to be heat energy. The second law of thermodynamics goes together with it. It says that when energy is transformed, The quantity of energy remains the same, but the ability to do work diminishes. So like I said, you put the gasoline in your car, you're going to get some kinetic energy, but you're also going to get some waste energy, which is in the form of heat usually. Okay. So for example, they're showing you how to do calculations for efficiency, and we'll talk about that in class. So energy efficiency is the ratio of the amount of work that is done to the total amount of energy that you gave to the system. For example, if you had a car that's 25% efficient, you're only going to get 4 gallons of energy out of the 16 gallons you put in there. 4 gallons is going to give you the moving energy. The rest of the gallons will give you the heat energy, the sound energy, the friction, things like that. So here's examples of using energy. We could use the same amount of, we could have the same amount of heat, but we'd have to use a lot more wood for a traditional fireplace. A lot of this energy that we put in a regular fireplace is wasted. That's why they're trying to make more efficient wood stoves that are going to give us a lot more energy. So wood stove is 70% more efficient than a fireplace. So regarding the second law of thermodynamics, we can talk about energy quality. That's how much useful work are we going to get out of something. And we also need to talk about entropy. Entropy means that in the natural world, things go from ordered systems to disordered systems, and that's just the way we found it to be. So it's a law. Entropy is a law. And it means that things are going from organized things into disorganization naturally, unless we put a bunch of energy into the system. So for example, if you go into your room and like say you decide to clean your room on Sunday and it's all perfectly organized, by the end of the week it's probably going to be a little bit disorganized. And that's the law of entropy. Just the gravity will pull things off your desk. Things will get moved around. It'll become much more random. You're going to have to on Sunday again go and take energy and organize your room. Take energy, physical energy, and move things around to the way that you want them to be. So entropy means disorder, unorganized. So energy conversions we're going to talk about all through this whole class. And we're going to talk about, say, this little lake right here. We're going to say we're going to put in heat energy, and it's going to change from a liquid into a steam. So that's the energy conversion right there. We're going to talk about all that in this class. There's 2 types of systems that we can talk about. One's an open system where things are exchanged between the boundaries of a system, and a closed system. So for the Earth, that's our system that we're talking about. And we're going to put in solar energy. We're going to get out, when we put the solar radiation in and it touches the Earth, it's going to give off heat. We're going to reflect some of the light, so those are outputs. That's for energy. That's called an open system, where we put things in, we get things out. For example, matter on the Earth is a closed system. We have a certain amount of matter in the Earth, and nothing is escaping it. So in general, we have a few things, like we've put out some satellites and things like that, and astronauts and things like that. But in general, Earth is a closed system for matter. There's another thing we need to talk about, which is called steady state, and it says that the input, the things you put into the system, are going to equal the outputs. So inputs are going to equal outputs. And it's not the same thing as chemical equilibrium. So chemical equilibrium, let's look at that real quick, says that that the rate of the forward motion of a chemical reaction is exactly equal to the rate of the reverse reaction. So if I have this pink chemical and this white chemical, this red chemical and the white chemical, and they make a pink chemical, then this pink chemical is going to break down and make those two again. So this is a chemical equilibrium, but it's not a steady state. So I have, for another example, I have pink and yellow. I put them together, they form this molecule right here, and then they also break down like that. Let's go back to where we were. A steady state doesn't have to do with chemical reactions. It's talking about physical things and energy as well. So the inputs, whatever input you're talking about to your system, is going to equal your output. So remember, a steady state in equals out. Those steady states can have feedback loops. And if you have a negative feedback, it's going to decrease the rate at which the change is happening. A positive is going to have increasing the rate. Okay, so negative is decreasing the rate, and positive is increasing the rate. And they don't mean good or bad. Negative doesn't mean bad. Positive doesn't mean good. So let's look at once you get the idea. Say we have a lake, and it's for a particular level of water. The level drops because maybe some people take some off of this, out of it. They use some of the water. Then you have less of a surface area. It gets smaller. It shrinks, and because it shrinks, it's going to have less evaporation from the sun. And because it has less evaporation, then the level is going to rise, and then the lake is going to go back to where it was before. So that's a negative feedback loop. Because you reduce the surface area, you have less evaporation. So negative means less. Let's look at a positive feedback loop. Population increases for a particular animal or humans. You have lots of births. The population increases. And because you have more population, then you're going to have more births overall. So this is a positive. So everything's going to start increasing, going more and more positive as a positive feedback loop. So this is increasing, this is decreasing, or staying the same. So we can have changes in a natural system. Natural systems naturally change, like the seasons change. We have changes in climate because of our Earth tilting and being farther or closer to the sun. Or I mean, the tilt is changing. Sorry, the tilt's not changing, but when we're spinning, we're getting more or less of the sun because of our angle. And you can have human-induced changes, and we're seeing that human-induced changes are really changing a lot faster than nature can deal with. So we're going to talk about that in this class. So that's the end of chapter 2, and I'd like you guys to, I'm getting to the page, I'd like you guys to read page 47 as well. And 48. Read the whole chapter, obviously, and then I need you guys to do the multiple choice questions on page 49, 50, and do the FRQs on page 51. Don't worry about measuring the impact. We'll do that on our own later. So I need you guys to do pages, again, 49, 50, and the FRQs 1 and 2 on page 51, and I'll tell you the due date. Thanks, guys. Talk to you later.